Okay. Hi everyone. Today we will work on a beam submitted to a distributed load that look like this. It's a first triangle and a second triangle. Okay, let me move them a little bit more. Oops, something a little bit more like this. If I can, here we go. Like this. Okay. Yeah, that's super easy to move after that. But you got it. You got it. Okay. No. Here we go. So we have this distributed load going down everywhere. Oops. Okay. We have the maximum of the distributed load will be 5 kilonewton time meter, and this distance will be 4 meter. It looks a little bit more. Okay, I will try to move that. Okay, and this distance will be 6 meter. Okay, and we have two connection, one pin connection there, and one normal connection there. Okay. So the question is, what is the shear diagram and the bending diagram of this beam? How is it submitted? So the first things to do is to find the reaction forces. So at A and B, what are the reaction forces? So to do that, we need first to find the resultant force of this triangular load. So let's do that. Step one, resultant forces. Okay. I put a S because we will do first the resultant forces of the triangle that is to the left. So we will do that triangle first, and after that the other triangle. So let's start with this one. Okay, so this one will be equivalent to, I'm drawing my beam again. Okay, so the first one, FR1, will be equal to the length time the base, or base time 8 of the triangle divided by 2. So 4 times 5 divided by 2, that is equal to FR1 is 10 kilonewton. And the distance, this is at 2/3 from the tip of the triangle, so from A, or 1/3 from the base. In this case, the base is like in the middle at 4 meters. So that would be at 2/3 of 4 meters, the distance. Okay, this is for the first one. Let me move that to the left so we can find now the resultant forces of the second triangle. So second triangle, this is the triangle that I will highlight in blue. This one there. Okay, on my graph, they looks like exactly symmetrical, but I don't make an example that is symmetrical. Okay, the one is 4 meters long, then the right is 6 meters long, just to show you that the equation will be a bit different. Okay, so FR2 for the second distributed load, it will be a bit more. Okay, this is FR2 because it's longer. So the 6 meters times the base, 5 kilonewton time meter divided by 2. So FR2 equal 3 times 5, 15 kilonewton. And the distance, that will be 2/3 from that side. So 2/3 times 6. So that will be at 4 meters from that side, from the right side. Okay? And okay, let me redo this one. We can even go one more step. We don't have to. We can find the reaction forces with FR1 and FR2. But I ask you in your homework to find the FR. So let me show you how we find the FR. So those two forces are equivalent to FR, okay, at a distance from A of X bar. Okay, so let's say that's the point A. So how do we find this X bar? And that's the question that you need to enter in your box. So let's find that one. we will do an equivalence of moment. So the moment about A of the first system with FR1 and FR2 is equal to the sum of the moment about A of FR. So we have X1 FR1 plus X2 FR2, that is equal to X bar FR. Oh, we didn't write FR. How much is FR? FR will be FR1 plus FR2. That will be 10 plus 15. That will be 25 kilonewton. So now let's do this equation of moment. X1, so just be careful. X1 will be there. And X2 will be there. Okay, always from the same point. Okay, don't change the referential. So X1 is 8 divided by 3, the distance. FR1 is 10. X2 will be 4 meters, so the distance of the first triangle, if we go back there, 4 meters, and 1/3 of 6. So plus 4 plus 1/3 of 6 times FR2. FR2 is 15 kilonewton, equal X bar times 25. Okay, and solve that, and we will get X bar equal 4.67, I think. Yes, 4 plus 2/3. 4 plus 2/3. Or you can keep it 4 times 3, 12 or 14/3 meter. Let's try to keep the exact number. I just checked those one. Here we go, that's correct. So now to find the reaction forces, remember we need to find the reaction forces. We are not done. We have our beam, FR equal 25, distance from A equal 14 divided by 3, and we try to find AY and BY. And this distance that we need there, this total distance, our two triangle load are 4 meters and 6 meters, so the total length is 10 meters. So sum of the moment about A equals 0 give us minus FR times 10, oops, not times 10, times 14/3 plus BY times 10 equals 0. And when you solve that, you get BY equal 11 plus 2/3. That is also 33 35/3. Okay. And sum of the forces on Y equals 0. We have the AY minus FR plus BY equals 0. So AY equal FR 25 minus 35/3. So AY equals 75/3 minus 35/3, 40/3. This is kilonewton, and this is kilonewton. Okay, so that's really the first steps, is to find those BY and AY. Let me highlight them, and I encourage you also to square your final value. That helps the professor to find them on your paper. So 40/3 on the left, 35/3 on the right. We have our beam. Let's draw our beam again. Oops. And we have now AY, okay. AY equal 40/3 and BY equal 35/3. Okay. So for the shearing force, for the drawing of the shearing force and the bending diagram, we need to come back at the beginning. We need to come back with that distributed load. Okay, so we can keep that distributed load, this drawing of this distributed load on top of that. Okay. Because of course a distributed load and the punctual force does not create the same internal effect inside the beam at every point. Our two systems, so this system and the one that we have on the left there, this one, is the same if we look at the external forces, but it's not the same for what's happening inside. So let's try to kind of not guess, but like starting to draw the shearing diagram. And oops, I know I'm trying to use the tools that are all provided. But it's a bit more than what I was doing. And where we'll have some changes, what is important to draw. Well, maybe I can do it in very light. I think that will be great to see. Up this line at 4 meters and this line at 10 meters. Okay. Ah, let me try to do it straight from there to there. Okay. So what we know, we don't know a lot of things. We don't know a lot of things. What we know for the shear forces, so this one are the force in kilonewton. And the second one, I will do it green. This one will be the moment in kilonewton time meter. Okay. What we know for the forces, we know at the beginning we go up 40 divided by 3, and we know at the end we go up, oops, 35 divided by 3. Okay, that's what we know. In between, there is some distributed load. We know that the flexion, like that will be a smile. Okay, I cannot go in the other direction. That will be a smile. So we know that the flexion will be positive somewhere like this. Okay. There is a place where the moment will be max. So when the moment will be max, where the shearing will be 0. So we may have something like, okay, but we don't know more than that. You will see, you will be used to, like, triangular load always give you a second degree order equation for the force and third degree order moment. We just need to go from 40 to minus 35 third with the progressions. There is no external load, punctual load, so there is no drop outside the first one at the both ends. There is no drop. Here in this example, there is no external moment. There is no fixed connection in the wall that can have an external moment. So our moments start at 0 and end at 0. It has to. There is no external moment possible. Be careful, my students, in your homework, there is an external moment on the left. So you will not start at 0, you will start at your moments there. Okay, but not in this example. So what we can do to draw those drawing and find like very precisely the equation, we will split our beam in two, and we will do 2 times the equation. So we will do from 0 to 4 meter, 0 to x to 4 meter, because the triangular load is, we can find the function of that triangular load from 0 to 4, and we will do from 4 to 10 meter at the end. Okay, so this 4 meters is decided by where is my force max on my triangular load. From 0 to 4, I have my beam like this. Okay, this is the point A, so we have the force AY. Okay, let me not do the force AY. I will have like one more drawing, because what we need to find is that this yellow load is not exactly all the way there. So we have that load like this. Okay, yellow, orange, and we have that distance that is x, but it's not 4. 4 is later. 4 is maybe there. Okay, this is the distance 4. So what we need to find is this value there. How much is that? Where is what is the force max? So we will make a similar triangle like this. We know that this distance is 5, and what we want to find is A. So if we apply the similar triangle rule, we have A divided by 5 equal x divided by 4. Okay, the total distance. What we need to find is A. So A equal 5/4 times x. This is my force max here. Okay, so this point there is 5/4 times x. So now I can draw my little piece of beam again, replaced by FR1, but just for x, just for the distance from 0 to x. And this is equal to what? This is equal to the length of the beam, that is x, times the force, that is 5/4 of x, divided by 2 because it's a triangle. This force is at the distance of 2/3 of x from the tip, and we have a y that is the 40 divided by 3 kilonewton, the ay there. And what we want to, oh, let me write the ay in blue, because, oh no, I want to keep that line. Okay, I will draw that force in blue because we know that force. What we don't know is the internal forces. Okay, so we found that ay. So this is the 40 divided by 3. Okay, and what we need to find is, let me keep that blue. I don't use too much orange. So we are on the right side of the beam. So V1x is down, M1x is positive, N1x is 0. There's no normal forces there. Let's keep it a bit more simple. And now we can do the, oops, can I move this one? Oops. I can do the equation to find the internal forces, the equations of the internal forces. So if we do sum of the forces on y equals 0, we have ay, we have 40/3 plus minus FR1. So FR1 is x times 5/4 of x divided by 2. So it's 5/8 of x squared. Okay, this is my FR1 x. And V1 is negative, so minus V1 of x equals 0. So the equation is V1 of x equal, move that there, minus 5/8 x squared plus 40/3. Okay, I double check that equation, and this is correct. So this equation there is this one. Oops, is this part from here to 4, and it stopped there. This point is 4 meters. Okay, this point is 4 meters. We don't know what the points with the 0 axis, with the x-axis is yet. We don't know that value. It's after 4. Okay, and to draw that, I encourage you, draw it in your calculator, like plot it in your calculator, in Desmos, anything, that will be the best. And now we can use the same free-body diagram to find the moment. So we have sum of the moment about x equals 0, give us. Okay, so we need also that full distance. This is x. So we have minus 40/3 times the distance x plus FR1x, that is the 5/8 of x squared. So this is the force times the distance, that is 1/3 of x. So this one is the force, this one is the distance for the moment. Okay? And plus m1 of x equals 0, because m1 of x is positive. So we have m1 of x equal minus 5/24 x cubed plus 40/3 of x. And this is the equation. Let me make it another color. This equation there will be from 4 meters to 10 meters this way. Oh, no, not this one, not this one, not this one. Not this one, not this one at all. Green one, this one will be, I would say, like, why is it not 35 third at the end? That will be this one up to 4. Okay, when x equals 0, the moment equals 0. That looks good. Let me write the equation that we found. So this one is v1 of x equal minus 5/8 x squared. I know it's too small, plus 43rd. And green one, this one is m1x equal minus 5/24 x cubed plus 43rd of x. Okay, I should move that one down a little bit. If I can, up. Zoop. So now I can maybe move that down. Here we go. This is awesome. Oops. This one. Okay. So that was the two easiest equation. Now let's work on, try to move that. Oops. Because I went a little bit too far. Let's do from 4 meters to 10 meters, and we will do the same step again. Okay. So now we look at the right side of the beam. Oops, like this. So remember, this total distance is 10. Now x is there. So this distance is 10 minus x. Okay, super important. Everything will be in terms of 10 minus x. Okay, and we have our load. Which color do we want? Let me do my color in purple. Like this. Oops, I need it way bigger. The same size. Here we go. Okay, oops, I need a bit more space. Here we go. So the question is, we know the length of that triangle, okay? But what is F max here? We need to find this F max. We will do the same triangle, similar triangle rule. So this length in purple was 6 meters, and the maximum force was 5. And what we try to find is the B dimension. So we have similar triangle rules. B divided by 5 equal the 10 minus x divided by 6. So we have B, that is the maximum force, distributed force, equal 5 divided by 6, 10 minus x. Okay, this is just your point there. So this is 5 divided by 6, 10 minus x. Okay, that was the step number 1. Now step number 2, let's find FR2x. So we have our beam. Oops, need more space. Up, our beam, and FR2x will be somewhere there, and it's equal to what? The length, the 8 of the triangle, so 10 minus x, times the force, so times 5, 6, 10 minus x, and everything divided by 2 because it's a triangle. Okay? And we will look at this distance from that side, because we will do x on that side. That will be 1/3 of 10 minus x, the total distance of the rectangle. What do we have? We have by, that is 45/3. Let me double check. 35/3. And we have our unknown. We are on the left, so V2 is up, and M2 is counterclockwise negative. I think we have everything. So now we can do our sum of the forces on y equals 0. We have V2 of x minus the FR2x. So let's simplify this. It's 512 times 10 minus x squared. You don't need to develop that. Keep it 10 minus x. It's really making more sense to keep 10 minus x. And plus 35/3 by equals 0. So V2 of x equals 512 of 10 minus x squared plus 35 third, minus 35 third. So when x equal 10, v2x equal minus 35 third. So let's check that. That's the one I was trying to do it a bit too fast before. So this one will be that equation. Here we go. So I say v2x equal, oops, I say 512, 10 minus x, 10 minus x squared minus 35 third. Okay. And let's use this Frobe diagram to find the moment. So we have sum of the moment about x equals 0. So about x, we have minus the moment m2x, because the moment m2x is negative. FR2 create a negative moment about x, so minus 512 times 10 minus x square. This is the force. Now we need time the distance. The distance is this one, time 1/3 of 10 minus x. So this one is a distance. Don't forget the distance is something that happens a lot. And the by 35 third create a positive moment. And this total distance that we don't have there that I'm adding is 10 minus x. So 10 minus x equals 0. So m2 of x equal 512 times 1/3 equal minus 5 divided by 36 times 10 minus x cubed plus 35 third times 10 minus x. Don't develop your 10 minus x, keep it this way. It's the easiest way. And this one, so my first part of the moment was green, I will make that one blue. This one is this part of the equation. Bloop. And you see when x equals 10, we have 10 minus x everywhere, that will be 0. So this equation is m2 of x equal minus 5 divided by 36, 10 minus x cubed plus 35 divided by 3 times 10 minus x. So, yep. So long equations, but they kind of make sense. And now questions. My question is, what is the maximum bending moment? And how do we find it precisely? Okay. So what we can do after we draw those diagrams and we draw them precisely, if we look there, let me make it yellow. There is a maximum there. And so this, remember, the moment is the derivative, is the integrals of the shearing. So where the slope of the moment is 0, I mean that the shear is 0. It's there. Okay. Oops. So this is the same point. Okay. And just like to come back on that, this is also why when the shearing force is positive, the moment increase. When the shearing force is negative, the moment decrease. Because the slope of the moment depends of the derivation of the shear. Okay, you follow me? So just remember, bending moment is the integral of the shearing force. So it's also the area below the shearing force curve. So what can we do to find the precise moment, the moment max there? Let's find where the shearing force is 0. And you can see our graph that the shearing force is 0 when it's with the function v2. So we will use the function v2 and solve for v2x equals 0 and find x. And after that, plug this x into m2x. So last step, moment max when v2 of x equals 0. So we need to solve for 512 times 10 minus x squared minus 35 divided by 3 equals 0. How do you solve that? Okay, you can go one step at the time. 10 minus x squared equals 35 divided by 3 times 12 divided by 5. There's a square root, so there's two options. You can go on your solver, on your calculator, and you can go on Excel if you want. I show you how I do it in Excel. That's what I use. It's easier for me because it's on my computer. But just be careful of that. Oh, there's also another option. You can plot that in your calculator and see where you cross the axis. Okay? Just be careful. There's two answers on that. There is an answer around 14, and there is an answer that is around 4.7. Which one is correct? 4.7, that cannot be 14. 14 is outside your beam. So when you do that with solver, your answers will be exactly, let me plug like the closest as possible. 4.7, okay, 08 meter, or 4.71. So this value there, this one there, is for x equal 4.708. Okay, and now I take my equation M2. Oops. There, my blue equation. So we have M2 of 4.708, and you replace 4.708 in your equation. So minus 5 divided by 36 times 10 minus 4.708 cube plus 35 divided by 3 times 10 minus 4.708. I know, oops. So you find M2 of 4.708 equal minus 41.16. This is kilonewton time meter. So this is your moment max. I know it's negative, but depending on your section, you need to find the moment max. Yeah, you may need to find the moment max positive and max negative, so mean. In our case, the moment, oops, is it positive? Oh no, it's plus, it's plus. I don't know, I found that there was this is plus. So in our case, the moment is positive, and remember our bar, our beam is in flexion like this. So little smiley guy, positive, and so we will be at 4.708 meter. Our moment will be the maximum there, and the fiber on the bottom will be in tension, and the fiber on the top will be in compression. So if you need to find your maximal normal stress, compression, and tension, that will be at that point, and that will be with a moment of 41.16 kilonewton time meter. I think that concludes what I have to say about those this example of triangular load. I know we did a lot of steps, but I think that's everything makes sense. Almost broke my chair. And yeah, go one step at a time. Find the reaction forces. Sometimes to find the reaction forces, you need to find the resultant forces first from the distributed load, and after that, cut your beam into segments where the distributed change. So here we make a segment from 0 to 4, and after that 4 to 10. Be careful where is x. Be careful what is your maximum triangular loads, because we cut it. It's not anymore 5 kilonewton time meter. It's smaller than that. So similar triangle rule, and take the time to write your equations. Don't forget your distance when you do the moment, equation of moment. Okay, I'm done with this video. I'm glad it went well. Let me know if you have questions. Bye-bye.